Okay, welcome everybody to today's digital control lecture. Right, so last time we started into the root locus method, and just for you to wrap it up quickly or to get into it quickly today, our task or our objective in this fourth chapter of the lecture is now that we evolve our tool set that we can use to design discrete time controllers. So we started out with looking into transferring controllers that we create by usual designs that we know from before, from continuous time control design, and basically add in the zero order hold delay, or the delay due to the zero order hold, and then design the controller and then go back into the discrete time domain. That's what we had, I think, 2 lectures ago. Last lecture, we started into the root locus method, and the root locus method is treated in the course feedback control in some more detail. The nice thing is it's exactly the same method as in continuous time control design. And that's where we step in today once again, and we go through some of the examples there, and then we'll go into what we call the model following controller here, MFC. That's another control structure that is particularly useful in some advanced control concepts. I'll get to that when we are done with the root locus design. Let's go into the root locus method once again. So just as a short reminder, the first task we have to do is basically look at our control system and decide for a sampling frequency. We can do that by looking at, one hand, we can look at Shannon. The Shannon principle, or the Shannon theorem, tells us that whenever we have some highest frequencies active in our system, in our signals, that we choose our sampling frequency or our sampling time less than 1/2 times 1 over this frequency that occurs in the system or in a signal somewhere, which is a 2-week bound usually. We should definitely sample faster, because usually we do not have the idealistic framework of Shannon valid. So when you look at typical responses, you see that up here of some non-oscillatory response like this one, or a typical oscillatory response. You can identify time constants, as you know, from PT1 behavior, or in PT2 behavior, the period length of a damped oscillation here. And then the rule of thumb that is usually successful is select the sampling time basically an order of magnitude faster than that. If you have several of those effects in the system, you have to decide for some trade-off, but you have to resolve the relevant time constants here fine enough. So with several samples at least. And usually we have 8 or 10 samples, which we consider sufficient. The Shannon case would resolve that with only 2 respectively, two periods, respectively 3 samples. So basically this up, down, and up would be the Nyquist frequency actually. So that's 2 cores, so that's the coarse end of what we can select. Okay, so once we've done that, we can go into the Z domain and have a system representation there. And I'll directly flip to root locus design. So the root locus design method, it's an analysis method and a design method that basically exploits the form of our characteristic equation and solves that in a clever way. That's about it. And to do control design there, we usually go for specifications of the control design. We formulate those first. So first we look into static specifications. I will just go over that quickly. We did that last time already. Basically, static specifications are, for example, the position error and the velocity error. And here are the formulations for the discrete time control system. You see this control system up here in this figure 4.7. So we have a controller in series connection with the plant in its Z domain representation, and a unit feedback, a negative feedback, and W is the reference, E is the control error, and Y is the output, and in between here we have the control input U, the manipulated variable. Okay, and the position error is defined as basically the value of the control error, E here, after we step up in the reference for long times, so for the limit for Z towards 1, respectively for the time index towards infinity. So we look at the steady state response when we go in with a step, that's the step representation in the Z domain, and then we just evaluate this limit, and the position error is just 1 over 1 plus Kp, and Kp is this stationary gain essentially for of the loop gain, Gd times G. And of course, if that's an integrating behavior, then this gain is infinite, and we will zero out this position error. That's asymptotic tracking as we know it. It's the same story here in discrete time. Velocity error, then what we can do is use the same formulas. We just go in with a ramp, a unit ramp, and then we have the corresponding limit expression, and we call this Kv the velocity error constant. And if you have specifications in the position or velocity errors, then you have some idea now how the loop gain should behave in its stationary limit. Okay, that's why we come up with these static specifications. For dynamic specifications, that's what we typically mean when we speak about some rise time, so a certain time that the system reacts and is being pulled up to the reference or to the target value. Then there is some settling process occurring. So basically, usually you have some overshoot, which we call here EM, as a ratio of the maximum amplitude here divided by the final amplitude, -1. And then you have the time at which this maximum occurs. Then you have a settling time after which you end up and all the transients have died out sufficiently well so that the output variable here is within plus minus some delta bound of the final value. This is typically 2%, plus minus 2%, plus minus 5%, or whatever you want to use. And these dynamic specifications, they are basically real world numbers that you can come up with. By that, you can specify how fast the system should follow a reference step or should adjust its behavior once disturbance hits. If you have a disturbance step, you will usually want to have the stationary value of the output either 0 or close to 0 if you have a step disturbance acting. But also there you can speak about a settling time, for example. Okay, and if we have these numbers, we can translate them into our well-known S domain and into a pole pair location of a dominant pole pair. So here the dominant pole pair idea comes in, because in the PT2 case where we've drawn down these numbers, we have simple formulas. So if we have a second order system which dominates the response, if we have two poles that dominate, and then there might be some other higher order dynamics, but they should not be important, then we can approximately treat our system as a PT2 system and specify two poles, two complex conjugate poles in S, and of course in the Z domain afterwards. We just transform them to the locations in the Z domain afterwards. But the step is usually first you translate these real world specifications in a dynamic setting, you translate them to the S domain pole locations, and then to the Z domain. So that's how we come up with the specifications to set up our control design if we, for example, if we want to use the root locus method. We have some formulas collected here for the rise time and the overshoot and so on. And in the collection formula, that's also included, of course. Then we spoke about, last time we spoke about first and second order system responses. And when we look at the Z domain first and second order responses, then what we can see is for the first order response, that's basically systems that look like that, C over Z minus P, which is basically a PT1 behavior. And if we look at its pulse response, so that's the weighting sequence that we look at now, we can see that depending on where the pole location is, if it's inside the unit circle, then we will get the typical response that we are used to. It's just, of course, sampled. And it's for an asymptotically stable PT1, we will have a decaying pulse response, a decaying weighting sequence. The boundary case, the marginal case, is when this pole tends or goes into the integrator location at Z equals 1. Then the pulse response is just basically the step. So we hit the system with a pulse, and the answer of the system is that the output jumps up to 1 and stays there. That's marginally stable. It doesn't blow up, but it doesn't decay to 0 as well. And then the next qualitative case would be to shift this pole outside of the unit circle, and then we have our exponential blow up. So that goes to infinity there. But then we've seen the interesting effect that when we realize a system with the pole on the other side, with a negative real part in the Z plane, so the case is here on the right, then we have a very interesting behavior, and we call that the ringing behavior. So we have essentially a change of sign in each and every sample. So it's flickering back and forth the output, you could say, or up and down. And that happens with actually a frequency, which is the Nyquist frequency, which is half the sampling frequency. And that's very interesting because it's actually an oscillatory behavior, but we have a PT1 essentially here, first order system. And it's intriguing that this happens actually to create an oscillatory response. This oscillation is always, in a sense, locked in at the Nyquist frequency. That's really coming from our sampling procedure and how the system is realized. And because it's the Nyquist frequency, it's usually we sample pretty fast. We sample much faster, as we've seen before, than the fastest expected responses in the system, and also as the usual system dynamics that we have in there. So if we are an order of magnitude faster than that, or a factor of, let's say, 4 or 5 something faster than that in terms of the Nyquist frequency, which is half the sampling frequency, then we have a very high oscillation frequency that comes in this ringing, due to this ringing effect. So if we have ringing, that means if the system exhibits poles on the left side here in the Z plane, then we get ringing. And this is very high frequency for our application. And that can be deadly, or it can be damaging to our systems, because imagine that's a mechanical system which has a very active actuator, and this actuator now hammers in at half the sampling frequency. That could be several kilohertz, and it really sounds like a construction machine or something quite violent. So we have to take care of that. We will see in several control designs that if we don't take care of that specifically, that we will get closed loop poles that are on the left side. And they may be really damaging or bad for our system behavior. And sometimes you have to look into the system signals to actually see that only. And we will have several countermeasures that we look into how to avoid that. All right, this also in some more complicated setup occurs in a second order term. So we have 2 variants of the second order term, which you will split apart. If you have some numbers here in the coefficients, you have to, and you want to get to this formulation and identify this omega t parameter or eigenfrequency basically. and this parameter A here as a decay rate, then you have to put it, you have to do comparison of coefficients, and you will identify an amplitude for this part that you see on this page, and for the part on the next page, which is yeah, basically just a phase shifted version of the same oscillation. And also here, we'll just stay in this particular version here. Also here we see qualitatively the same issues. We have usual non-ringing dynamics here on the left. If the pole pair is on the right-hand side and it's either inside or on or outside the unit circle, respectively, we get an asymptotic decay. You can imagine this this decay rate is like an envelope here that pulls it together. Here we have this envelope as being a constant amplitude over time. And here we have the exponential blow up of this kind of trumpet, and it goes to infinite amplitudes. On the right-hand side, we see that if the pole is, has a negative real part here, then we see this ringing behavior, and it looks a bit different in this sense, but we also see that from one sample to the next, we have a relatively large jump in the value, which is also associated with a change of sign here. Then there is basically very little going on, and then there is a change of sign again. So also this ringing is, of course, something that is quite, that has high frequency content here. All right, that's for afterwards when we look at certain responses to see that there is ringing and that we should take care of that. We'll have that in one of the other control designs and examples. Now, let me go back to the root locus method specifically. Essentially, we look at the unit feedback system here, and we have the loop gain, which we call GO. That's usually coming from German literature here for open control circuits, G offen. In English literature, you will usually find L for the loop gain, which is just, yeah, GO, which is the same thing. And now if we have this unit feedback here, negative, then we know that our characteristic equation is of this form, GO, loop gain plus 1 equals 0. And we've discussed last time that this is a complex valued equation, an equality in C, and the complex numbers. And there it's scalar, but it's complex. So if we look at that and want to solve this, or want to ensure that we solve this equation fully, we can either split it up into real part and imaginary part, so in a Cartesian form, and ensure that both parts, the imaginary part as well as the real part of the equality, are fulfilled. But we can also take an Eulerian approach. This Euler way of writing down such a complex equation or equality is actually advantages here, because it turns out that we can split up into the argument, which we call the angle condition, and into the magnitude condition. And that's, of course, we have to fulfill both to fulfill the entire equation here. But when we unwrap the terms in there, we see that we get terms where we have distances from the variable z that we enter with here. We enter with z here. So we have z coming in here, and then we have the zero locations and the pole locations of the loop gain, which we consider that we know a priori. We can evaluate that. We know our plan, and we can at least write down how the controller should look like. And what we want to find is, of course, the poles of the closed loop. Where are they? And we want to ensure that they lie somewhere where we want to have them, which is not an easy task. And that's why this method actually is good if it's simplifying this task. And it simplifies it in the following way. The angle condition turns out to be independent of the unknown gain K. K is just the proportional gain inside here, and usually we can attribute that to the controller gain. And it only pops up in the magnitude condition, but it doesn't pop up in the angle condition, except for its sign. And that's what we usually can decide about, or if we're unsure, we can, or if we have to look at both signs, we can do that separately. But we don't need to know K here, the specific value of K, in order to evaluate the angle condition. And now what does this mean? If we fulfill both of these conditions, it means that for the chosen value of Z, we established that this equation is fulfilled, so that we know now that this value of Z is a pole of the closed loop. All right, and the nice feature of this method, the root locus method, is that it actually allows us to write that down in some parametric form, in that sense that we will get curves, which are the root locus curves or branches, that tell us where these locations of the closed loop poles that fulfill this equation can be. And we go through this curve by changing the gain K here. So basically for all Ks, it's like if we evaluate the closed loop poles for a fine grid of these K values. We can do that. We can draw plots with dot cloud basically, but we can do that in some more elegant fashion here, and we can use it for design, which is particularly interesting. Okay, essentially to understand the angle condition, it's important to understand what these differences here mean. These differences mean that we look at some value of Z or some branch where the closed loop poles will lie with some choice of the gain K. And we choose a particular Z now, and this is, for example, a Z location which corresponds to some desired pole location of the closed loop. That's where we want to get by designing our controller. That comes from specifications. And now if we know that where this Z is, we want to make sure that we actually put that Z on this branch so that we fulfill in the first place the angle condition. So we can write down the C here, and we know all the numbers of the zero locations and the pole locations of the loop gain. And we have to make sure that this is actually fulfilled, so that this left-hand side has to be a certain multiple of pi in radians. So the first thing we will do when we design a root locus controller is, with the root locus method, is we will write down our configuration of zeros and of poles here in the Z-plane. Then we draw the location of Z where we want the closed loop pole to be from our specifications, and then we determine these angles here. And it might be that one of these angles, like the one here, is actually unknown, and we can determine that now very easily. This Q mu here, for example, could be an unknown controller zero, which we have to decide for where we put it. And it's very elegant now that we can actually do that without knowing the specific value of the gain K here. And this by just making sure that this angle is just of the right size so that we can fulfill the angle condition. So that will be the typical first design step that we do. And by that, we know now where exactly the controller zero should be. And then we know all these zeros, and we can go into the magnitude condition and resolve it simply for K in order to make sure to determine which value of K corresponds to the pole location exactly here in Z. If we would use a different location of K, we would slide somewhere on this branch because all these other points here are also poles of the closed loop, but they are associated to different choice of K. Okay, and that makes it interesting. Afterwards, we'll have some discussion about that, what we can read off from these branches. We also collected some rules for drawing those root loci, these root locus curves. Here, these rules, I will not train them with you now here, but we will now and again talk about these rules when we look into the examples afterwards. MATLAB, of course, supports drawing root locus curves and doing root locus design with two different tools. I'll just write them down quickly here. So in MATLAB, you will have R locus to draw the root locus, and RL tool is an interactive tool to design controllers using the root locus method. Okay, design root locus controllers. So you can try them out, of course. This interactive tool has a nice help, so you can just play around with it. Yeah, I will jump to these rules when we need them. Essentially, let's go into an example. That's where we stopped last time. So we will look at this structure here of the feedback system, of the control system. So we have the controller, then we have the plant, and we will get some particular plant here. Actually, that's already GO, that's already the loop gain. So we have already some controller, which is characterized here by KP, by some proportional gain. And there are no other unknown parameters. That's terms which come from the plant. And this one may be an integrator from the controller, for example, or it may be an integrator in the plant. Now, the first task will be to construct the root locus curve for the system. And the second one is we want to determine which critical gain KP there is, which value of KP we will have at the stability limit. So if all the poles of the system are, or if poles of the system become unstable or marginally unstable, when we just arrive at the unit circle in the z-plane with the closed loop poles. And also, we want to determine the controller gain Kp when the closed loop poles, the pair of dominant poles, will have a damping ratio of zeta equals 0.6. So some particular choice of damping ratio. To do that, first step is we put it into some standard form. So we define the K here. If you look at this here, we want to make this coefficient here in front of Z, of the highest power of Z in the numerator, we want to make it equal to 1. So we just collect Kp times 0.3679 here into a new variable that we call K. And we will work with this K. And then, of course, when we want to know about the actual Kp, we have to insert here. So when we do that with K, we write the loop gain like this here. So we have Z plus this 0.7181 is, of course, this 0.2642 divided by this term. And the denominator remains unaffected. From here, we can read off directly the poles. The poles are down here. Remember, we look at positive powers of Z for the poles and zeros of a transfer function. So we have the one pole here is Z equals 1, which is the integrator pole here. And then we have another pole, which is at plus 0.3679. So that's the two poles in the system. And then we have a 0 in the system, which is at minus 0.72 roughly. Now, the first thing I said is that we draw basically the closed loop, the loop gain pole and zero configuration. So what we'll do now is we'll do exactly that. I will draw a pole here at 1, which is P1. Then I have a pole at 0.37, roughly 0.4, that's somewhere here, P2. And then we have Q1, which is at minus 0.72, which is somewhere here, let's say. Sorry, I want to draw the zeros with this ring. All right, now, what we know from when we look at the characteristic equation, let's think about that a bit. We have the loop gain GO of Z. Let's say we write that as some polynomial of B of Z divided by A of Z. And we have our characteristic equation, which is GO of Z plus 1 equals 0. And as you know, when we can write that down now in terms of B of Z divided by A of Z plus 1. Now we can multiply that by A of Z. So we get B of Z plus A of Z equals 0. So that's just a different way of writing down this characteristic equation here, or this one here. So what we did now is we've rewritten it, which used to be here a fractional form into a polynomial form. Okay, and now what you can see is the following. Let's say we write down the gain k here in the front of GO. Then what you see is that this gain ends up in the numerator here, and also here in the at the numerator polynomial b. And now if you look at this equality is fulfilled for closed loop poles z. So if z is a location of a closed loop pole, then this equality is fulfilled. Now if we set k to 0, for k equals 0, you're looking actually at the pole locations of the open loop. Well, that's clear because k equals 0 means just that we just opened up the feedback loop, and whatever poles have been in the system in open loop are still in the system in the closed loop. So then we get, just from this equality, we get A of Z equals 0, which is the characteristic equation of the loop gain itself, without closing the loop, of the open loop gain. So that means for k equals 0, that our closed loop poles are actually at the locations where the open loop poles are. Now, if we increase k, that will become some complicated function, and C will be something that will actually be characterized afterwards by the root locus curves. But for the limit of k towards infinity, what happens is that actually this term A will actually become less and less important to contribute here. So something very large times B is approximately equal to 0. So essentially for k towards infinity, this equality will end up telling us that B of Z equals 0. Okay, so that's why we see that if we crank up the gain k to infinite values, to very high values, then the closed loop poles will approach the 0 locations of the loop gain. That's why we will end up here. With one of the branches, we'll end up here. And with another branch, we'll end up somewhere at infinity. That's the zeros at infinity that we talked about 2 lectures ago. So essentially, I will shortcut it a little bit here. What we'll have is, for k equals 0, we'll start out our branch in the open loop poles, and we will go out of the open loop poles to some direction. You can refer to the rules to determine which direction that will be. So it goes out from there. At some point in this case, we will converge here to some common point. And from here, we have a so-called breakaway. We'll not construct it fully now, but essentially, we will get qualitatively something like this. So we get a curve that breaks away and that's recombines somewhere again. And it should be symmetric with respect to the real axis. So that's the real axis and that's the imaginary axis, of course. And then we'll have further and further increasing k, and one of the poles will move here and the other pole will move out here to the left towards infinity. So essentially we can read off of such a chart. We have this here plotted nicely. We can read off where these the closed loop poles will lie, and the further we go on this curve, it's associated with increasing and increasing values of the loop gain k. So we start out with 0 gain, then with very small gain, the poles will shift slightly. At some point, we'll arrive at this breakaway point. The poles will split up to two symmetric poles, some complex conjugate poles, and at some point will cross over this zeta curve corresponding to zeta equals 0.6. Then if we continue increasing k, we'll at some point here hit the stability limit. And then if we further increase the gain, we will have an unstable pole pair which recombines here again. And then at some point it gets becomes two poles here, one shooting off to left minus infinity, and the other one actually coming into approaching in, closing in on Q1 here. Be careful, that doesn't mean that once we've entered with very high gains here from the left, the unit circle again, that we arrived at a stable closed loop, because one of the poles is here, that's true, and it's only two poles in the system, but the other pole is somewhere very far out here on the left. So that's definitely an unstable system. And essentially, this tells us that when we look at the structure of these curves, we always have to make sure that we have no pole which is outside the stability region. And if we know that we have two poles here, we start out with an integrator and with this real pole and increase the gain k, then we see that for small gains, everything is fine and the system is actually stable. Here we get this particular damping value here for this particular value of k. And then if we increase it further, we'll get a maximum critical gain k, after which either two poles here on these branches until here, or one pole when we have a high enough gain so that one pole enters here again, but the other one is very far out, is unstable. So only up until this critical gain we'll get a stable response of the system. Okay, now let's determine this. We can do this graphically in this example, and we'll determine it in a mathematical way in the next example. So we see that you can do that in MATLAB, for example, in the root locus tool, by dragging the corresponding pole marker here to the stability limit, or you can switch on the grid, the zeta grid, and pull the handle here to this intersection with this curve. And then basically we read off the value k itself in our standard notation, which is 0.88 here for the critical case, or 0.15 for this case for zeta equals 0.6. And then we have to translate that back. Remember, we had this factor of 0.37 or something in between. Where was it? Yeah, here, this equation here, of course, connects k and kp in our case. So let's look down again. That's how we get to this critical kp value and the kp value which achieves a damping of 0.6. All right, so that's how we can interpret these root locus curves. And it's essentially looking at the parameterized figure or illustration of where the closed loop poles go when you change the gain of your controller, for example, of the loop gain in the end. We can evaluate that all if we take this this gain associated to a damping of 0.6, then we can evaluate the closed loop transfer function here and plot, of course, the step response, and we see that that's what we would expect. We have a nicely damped system response, slight overshoot, which is typical for a zeta value somewhere there, well between 0 and 1, 0.6. So we have some overshoot, but it's quite limited and it quickly dies out. All right, let's go to the next example, 4.4. So we have a transfer function. Let's start here in the S domain. That's the transfer function of the plant. We have 30 over S plus 2 times S plus 5. And now we want to design a discrete time PI controller to fulfill some specifications. So we want to have a zeta of 0.5 of the dominant pair of poles. Now we have to be careful because we will have two poles from the system here, and we will have an integrator from the PI controller. So we'll have a total of 3 poles And we have to make sure that we look at the dominant pair of poles. Essentially, the third pole location will have to be fast enough. Also, we choose the sampling frequency as 10 times the damped eigenfrequency, and the sampling time we choose as 0.25 seconds, so quarter second. Now we take this plant transfer function and transform it using the zero-to-hold sampling method into the z-domain. So again, in MATLAB, we directly take this GS from here, and in MATLAB, we would issue GZ equals continuous to discrete of GS of S and the sampling time capital T. That would be the MATLAB notation. And of course, we have our formula somewhere up there, which is 1 minus c to the minus 1 times the z transform of gs of s divided by s. That was this boxed equation somewhere 2 chapters back. Okay, we get to this formulation for g of z. So we see that we have a 1, 0 here. That's just the plant. We'll still add the controller, and we have 2 poles of the plant. Now we see again that we can extract this factor here and rewrite the system with some k. Here is the correspondence. So k. Then we have a real 0 in the PI controller, z plus a. A is unknown as of now. Then this comes from the plant. And we have the integrator pole, and again we have the poles of the plant. So that's our loop gain now, with an unknown 0 in the controller and an unknown gain of the controller. Okay, now let's work on our specifications. We have a specification up here, zeta equals 0.5, and we have a relationship between damped eigenfrequency of the closed loop system of the dominant pair of poles and the sampling frequency. So basically now, as we have the sampling frequency determined by a quarter second, we can come up with omega d and directly go into the formulas. Here we have the formulas which tell us where the poles are. So that's the absolute value of the poles, 0.7. It's inside the unit circle, of course. And the argument is plus minus 36 degrees from the origin in the z-plane. And by using tangents, for example, sine, cosine, we get to the Cartesian notation. So we know where the poles should be. All right, now in order to get, one difficulty now is that we have the unknown 0 location in the controller. We could start our control design as we did earlier on. We could start our control design by just choosing some of the stable poles and putting the 0 of the controller there in the hope that they will cancel out and simplify the entire task. But it can be that we cannot fulfill basically our set of specifications with that. So we will choose A in some very elegant way with the root locus method now. And that works as follows. We use the phase condition to determine A directly, or quite directly. Let's see how we do that. First of all, here in this figure, you see the configuration of the poles in the closed in the loop gain, in the open loop gain. So we have this pole is the integrator. No, sorry, this is the integrator pole, and then we have 2 poles here of our plant. Let's quickly have a look where these poles are. They are written down somewhere up there. Here we have them. Here are the poles. Let's just write them out. So we have P. Let's get the numbering right. PC for the controller pole is at 1. Then we have P1, that's at 0.6065, and P2, that's at 0.2865. If we insert either of these poles into the numerator, into the denominator polynomial here, you zero out the polynomial. So that's the poles directly of the loop gain. Also, we have Q1, we know that it's at minus 0.5586. That's from up here. And then we have another one, the controller 0 location, QC is at minus A. Careful, it's a minus A here. Okay. Now we draw the configuration. We just really put in here in a sketch which actually has the right distances here. So this one is at C equals 1. And we draw those. And what we don't know yet is, of course, where the controller 0 is. So we can draw it anywhere. This controller 0 here, it's anywhere, but what we'll do now is we evaluate the phase condition, and by that we can reformulate it actually directly to phi QC, so to the angle spanned by or through the 0 of the controller. And by that, by knowing this angle, which is, we insert, it's almost 90 degrees, it's a little bit less than 90 degrees. We see that this 0 actually is almost beneath Z1 here, and we can come up with the actual value of 0.555 here. And we did not need to look at K, other than we assume K is positive here. So that was done here implicitly for K greater than 0. And that's why we have this minus 180 degrees here. That's comes from the right-hand side of the phase condition. And we'll get all the other angles added in here with the corresponding signs. Here we evaluate it in degrees, and we get to phi QC is this almost 90 degrees. And we didn't need to use the value of K. Now we go on, and we can determine the value of K by evaluating the magnitude condition. And with this magnitude condition, it's fairly simple. We just come up with the distances here. Essentially, what you need is to measure these distances here. These distances from each pole to each 0. And of course, also now from the new one, the newly found. It's now not exact what I draw here, but you get the point. Okay, so these distances, the red lines, the distances of these red lines are the quantities that you need to insert into the magnitude condition and reformulate that correspondingly, and you obtain K. Okay, now we actually did everything. The only thing that is left to be done is to check whether we actually have a dominant pole pair now. And for that, we write out the characteristic equation, which is this third order polynomial, all numbers now. And we already know two poles, namely these ones. That's what we ensured already. So we can divide by these two poles, and we will get as a remainder term the result C3 equals 0.52. And it turns out that the absolute values, that's indicative of how fast these are, is significantly less than the absolute value of these other poles, of the pole pair. And by that, we can say that it's basically a dominant pole pair here. You could also, of course, translate that back into the S domain and check the real parts and how far they are to the left. All right, if we look at the root locus, in a root locus plot, it looks like this. So essentially what we'll get is we will have these rounded dots here as the specific locations of our closed loop poles. So we have these 3 poles here in the closed loop with our choice of k. K equals, what was it, 0.25 roughly. And we see that 2 of the poles end up at the curve zeta equals 0.5. So we have this particular damping. And then we have a real pole, which is faster. And that's fine for us. Of course, it's only approximately dominant. It's not that this 3rd pole here doesn't have any effect at all. So it's not exactly the response of a PT2 with these pole locations. But again, we just can simulate and check if we're close enough. Let's do that here. We look at the closed loop transfer function, the reference transfer function, and the step response in that. We see that we have some particular overshoot. It's now also visually, it's more overshoot than before, but before we had a higher damping in the other example. And in this example, we have a damping of only 0.5, so a higher overshoot is to be expected. But also here, it's essentially what we expect with these specifications. All right. Coming to the last example here of the root locus method is, let's see, we have a plant transfer function in the S domain again. This time we have a dead time term here, time shift, the delay in the S domain. We select a particular sampling time. We make sure that sampling time is significantly faster than the damped eigenfrequency. And we have some zeta of 0.5 again that we want to have. We take this plant transfer function, we decide for a PI controller that this decision can be based on, for example, static specifications that we require the system to have asymptotic tracking, so 0 position error. Then we need an integrator because, of course, here is just a proportional plant transfer function. So we need an integrator in the loop, and that's why we would decide in that case for a PI controller, for example. Okay. Again, we apply the zero-to-hold sampling. We arrive at our Z-domain transfer function of the plant, which has this structure here. And observe here now we have 2 additional powers here. So basically there is an additional factor of z to the -2 in here, which comes from the dead time term. And if you remember, dead time in the continuous domain was e to the -t dead time times s. So in this case, t dead time equals 5 seconds. Now I'll leave out the seconds here because it may be confusing with the letter of with the complex variable s. Be careful when you look into literature in that regard. Units are usually written in upright writing, in upright form, whereas a variable like our complex variable s is usually written italics. That's also done in our lecture notes, and you also can see it here. The complex variable s here is written in italic, and here as well. Whereas whenever it refers to a unit like this in seconds, or sampling to an abbreviation, then it's usually written in upright. That's a notation which is often adopted. Okay, so we have our plant transfer function here. We choose our controller, that's a standard PI controller. So we have, again, a proportional gain, we have the integrator, and we have 0 location in the PI controller to be determined. Okay, now again, we take, we put that together, we get to our substitution here so that we integrate this factor with Kp into some common K here. And then we can write down our our loop gain transfer function as this K times z plus a, 1, 0 here, divided by a bunch of poles, and the dead time here turns out to be to generate poles in the origin, double pole here, because we have 2 samples dead time. We can identify that we have a pole here at 0.3679. Then we have another pole at 1 from the controller, and we have 2 poles in complex 0. And we have 1 real 0 at the location -a. For the specifications, we get 0.5 as a zeta requirement, and then we have this fraction 1/12 between sampling and damped eigenfrequency. So we get pole locations which should be at an absolute value of 0.74 at 30 degrees separation from the real axis. So we get the Cartesian writing, we get this location of the poles of the closed loop. Now, let me just clarify that in this sketch. So we get, I will take one color for open loop values maybe. I think that's easiest. Let's take open loop values here in blue, open loop poles in blue. Then I take green for the open loop 0, and I take orange for the closed loop locations. So the closed loop is Z, that's what we want to end up with. And for the open loop locations, we said our poles are in blue, and the 0 here is also unknown as of now, but again, we will use the angle condition, the phase condition, in order to directly get the value here of this angle, phi QC, to fulfill the angle condition. So that's the formula for it. Again, we look at k greater or equal, or k greater than 0. And that determines basically if we have a shift of 180 degrees here in the phase angle condition. So we get, we can reformulate the phase angle condition to express phi QC directly. It's roughly 68 degrees. And from that, we can actually establish where this 0 should be. That's the first step. And in this step, we didn't need anything apart from knowing that k should be positive and the other known poles and zeros. Okay, once we've done that, we know now that in green, our QC is determined as at roughly 0.5. And now we use the gain condition to come up with the values of K, respectively Kp, to really realize the pole here at the specific location that fulfills our requirements, our specifications. Then we formulate the closed loop transfer function, which is GW here, for example. Of course, as an intermediate result, we'll directly insert into the controller transfer function. So that's the controller that we need, that we designed now. That's the main result. And now we analyze the closed loop response. We see that we have many poles here in the closed loop. We have 4 poles, and we have to make sure that all these 4 poles, or 2 of those 4 poles, are at our specified location, which is true if we've done the design correctly up until now, but we also have to make sure that the other poles do not interfere and leave the 2 pole pair, or the pole pair that we designed for dominant. Let's have a look. So essentially, what we see here is that these poles here are the ones that we designed for in terms of a dominant, of the dominant assumption, that we assume that this pole pair dominates the response. And then we have 2 other poles here and here. And yeah, the question is now, we can put them, we can take them back into the S domain. Sorry. Okay. You can take them now into the S domain and judge about them where they are. But the more poles you get, the more you actually have to see in a validation whether you are close enough to your PT2 idealization. So in the end, we'll have to come up with a simulation like here. And we look at the step response. Of course, we have 2 samples that time. That was what we modeled already in the plant. And then we have the response, and actually this response also looks qualitatively very nice, like what we would expect from a PT2 with the specifications. You can always plot the corresponding PT2 and directly compare how the perfect PT2 would actually be behaving. And in that sense, the design can be considered successful. All right, so that was a quick tour through some control designs with the root locus method. So essentially, what you should have as a takeaway message is the root locus method is some structured tool in order to look at the closed loop pole locations, which is essentially what the difficult thing that we solve for in a very elegant way. And we can see actually these, we can interpret how the system reacts when we change the gain of the system, where the poles will slide. That's actually why you would use root locus methods, because you get some more idea of how the system behaves, how sensitive it is. In the other course, in the feedback control course, we have some more examples and some more ways that we can apply this method. For example, for sensitivity analysis, when we ask ourselves the question, let's say our plant is, we write down our plant pole here from some data sheet, but maybe this pole actually changes afterwards and the system becomes slower or faster over time because of aging or of accumulating dirt, friction, damage, whatever. Then you can actually rewrite all this root locus method to actually assess how far this change of time constants can go until you're unstable, for example, which is a very interesting way of approaching sensitivity and robustness. All right, we don't do that now here. We will flip to the next control design method. But just as a teaser, if you want to know more about the root locus design method in detail, go to the other course, to feedback control course. There we treat that in some more detail and in the examples therein. And of course, in MATLAB, you have plenty of tools. The root locus tool, which is interactive and allows you to shape for simple controls, for simple control designs, and for relatively simple plants. It's a very useful method to play around with. Okay. If you have any questions, just post them and we can collect them afterwards, and we can answer them afterwards as well, of course. Otherwise, let's flip to the model following controller. This controller is a more advanced control concept than we're used to up until now. If you remember, some time ago when we spoke about pole placement in the basic course, for example, we've seen that we can change the pole location in the closed loop, which is what we did just now as well in the root locus examples. But what we do not do usually is look at the numerator of the closed loop dynamics. We didn't do that because it's in a particular sense it's less relevant, because it doesn't affect stability or it doesn't say anything about stability. But the numerator contains the, let's say when we manage to prescribe the pole locations as we want, as we desire in the closed loop, still the numerator plays a certain role in how the system reacts. And now the idea of the model following controller is to expand this pole placement idea and to shape both the poles of the pole locations of the closed loop as well as the zero locations. And by doing that, what we actually do is effectively, I will just draw a new system boundary here. And this system boundary is the entire closed loop, right? So enter W from the left, output Y on the right, the closed loop reference transfer function in this sense. And for disturbance, there is, of course, there is a transfer function as well. But looking at this reference transfer function, actually it would be nice to make this, to design a controller that actually achieves an entire desired transfer function instead of only desired pole locations. So actually what we want to have is GW desired of Z here. And the model following controller is actually a control design method or a control structure that tries to accomplish that. So that works by a more complex structure. If you look at the controller structure here, we not only have something here in the feedback path, so it's split up here between the feedback of Y and this forward path here, but also we have some polynomial block here, f of z, and all these three blocks together, they give us a lot of degrees of freedom in the design, and we will shape the design and we'll come up with formulas for all these polynomials. There's polynomials in here in z, respectively z to the -1, p, q, and f. And we will come up with formulas for all these coefficients in there. If we've solved these formulas, then we get all these polynomials and we can actually write down the entire controller transfer function from the inputs y and w to the output u. And if we've done that and plug it in the loop like so, then we actually will get, we'll make the system, the plant back here, really behave as our desired transfer function that we base our design here about. So it's a richer design than what we used to. And let's just start out by writing down. Remember that the block diagram is just a graphical expression of equations. So we just write out these equations. And that leads to the equations that we see here. P times U. So basically, you can write U equals 1 over P times WF minus QY. Okay, so that leads to this form here. If you put, if you multiply by P, then yeah, that was actually exactly 428, respectively this one when you reformulate it. And we specify that we have polynomials f, p, and q. We just decide for some notation here. So we decide for negative powers of z everywhere. And we write down f of z is some f0 plus f1 z to the -1 and so on until some order, which we don't know yet, but we just write it down as an ansatz, f nf as a coefficient times z to the -nf. And we call that the pre-filter or the pre-filter polynomial. Then we have a feedback polynomial q of z. We write it down in basically the same fashion with unknown coefficients here. And then we have this polynomial here, the feed-forward polynomial p of z. And we decide here for a particular structure, we set this first term, the first coefficient here, to identically equal to 1. So this polynomial is called a monic polynomial if it looks like that. And then we go to some order with negative powers of z. All these coefficients are unknown in the beginning now, and we will find a bunch of formulas to determine all these coefficients afterwards. Now, if we take, let's say the plant transfer function is given like this expression, y is explained. You see that here z is added to the output of the plant here to get to our measured output. So that's just how we model the disturbance here. So z plus b over a, that's also polynomials, times a dead time term, maybe z to the -d, times u. And a and b are also written down in this negative powers of z form. And a is also defined to be a monic polynomial. So this leading coefficient here is 1. And of course, the remaining coefficients, if if we have some scaling, then of course that ends up in the B polynomials. But we can always get to a form where A is a monic polynomial with this leading one coefficient. Also, what we have is that B of Z is always of lower order, in the sense that if we write it in positive powers, it's of lower order than A. So that if we rewrite it in negative powers, we'll see that B0 here is always dropping away. So we start out here with B1 times C to the minus 1, and so on. Okay, that's all notation up until now. Now let's do the interesting derivation, actually. So what we do now is we write down the closed loop transfer functions y as by a transfer function of the closed loop times w plus a corresponding transfer function times z. Here we choose the structure so that we actually have a disturbance transfer function. And we use our polynomials, our ansatz that we had up here, this structure in figure 410. And with all that inserted, we get these transfer functions. The transfer function that describes y with an input w, respectively z, and also we have a transfer function that describes u with an input of w and z. Now we'll set z for the sake of the reference design, so we forget about the disturbance for a moment. And by doing that, we get the reference transfer function here, which is just this term. So it's some polynomials multiplied in the numerator and then some polynomials multiplied in the denominator. That's all polynomial multiplications. So that's actually what makes things difficult here, because we have some polynomial b and some polynomial f. F is entirely unknown and they are multiplied together. So it's not so easy to actually style this polynomial f directly. And also we get polynomial p and q and they add up here. So it gets a bit messy and we have to organize how we solve actually. For in the end, what we want is actually that this GW should be equal to some GW desired. And then we have to fetch out the corresponding values of F, P, and Q coefficients. And that's our control design. So that's what we want to do now. That's the model following control design, it's actually called. Okay, now how can we do that? First of all, we cannot choose any GW desired to be realized by such a structure, but we will have to make some adjustments, or we have to take care of which GW desired we want to choose. First of all, we see that actually in the closed loop, we actually will see the dead time term coming up here in the numerator, so we can pull that out here. So it's quite plausible that we will not be able to cancel that out. So the dead time has to stay there, that the plant inserts or introduces. The next step is that we'll see afterwards that we have to be able to solve the corresponding equation. So if we have a GW desired, if this should be equal to GW desired here, then we have to solve uniquely so that we get a comparison of coefficients essentially. So we have to have a sufficiently high order here in the numerator and in the denominator to make all these coefficients fit to successfully to our desired GW terms. And to do that, we will introduce an additional degree of freedom. We introduce a so-called observer polynomial, AO, which we take as a monic polynomial again, and of certain order. We'll see what this order has to be afterwards, but we will just expand essentially both sides of the desired polynomials, so to actually accommodate sufficient order that we need here in order to have this correspondence. Okay, now if we have in GW, if GW is actually contains in its denominator process zeros already, then the order actually decreases. So we will do that in the following form. The process zeros can be written down like so. We can write down the numerator polynomial here. We always have a leading factor of c to the -1. Remember, we've said, let's scroll up here. Here, we've said that the numerator polynomial of the plant should look something like this. So we have b0 equals 0, that's gone here, and the first term is b1 times c to the -1. So we can always write down b of z as z to the -1 times something else. And then these two polynomials here, we can factor them basically and collect them into groups of b plus is what we actually want to exploit and to cancel. That should be those zeros of the plant that can be cancelled. And if you remember our discussions earlier, that can be only zeros if they are cancelled with poles which are inside the unit circle, which correspond to stable dynamics in terms of pole locations. So we will take into B+, we'll take the plant zeros that lie inside the unit circle, and in B-, those that lie outside, or just the remaining factors that we need. And those will just remain in the end. And if you go down here, when we put that all together, we have GW, which is BW over AW times C to the -D. We said that we need to have the dead time still in there. Now let's let's go from let's look at this term directly here. This term contains now our structure that we derived above. F times B, all this here is B, times C to the -D. And down here we have something split up of P times A plus Q times B times C to the -D. So that's this, this term here comes from our structure of the controller. By the way, here we write down P as a split up of B plus and P tilde, some other P tilde here. So as P was unknown, we said now that it's beneficial if we manage to do cancellations in the numerator of the plant here, in the numerator. And essentially what we can cancel is this B plus. So we will write B plus as a common factor in P, and the rest is P tilde here. So we just do the split up and substitute P by this form in here. You see that here. And now we have B plus as a factor everywhere in all these terms. So here it's a summation, of course, but we can collect this factor out of the summation and cancel this B plus is up down there with the B plus up here, even though it's a polynomial. And we end up with this form on the right-hand side here. So it's P tilde A plus Q Z to the -1 B minus Z to the -D. And in the numerator we have F Z to the -1 B minus Z to the -D. And if we go all the way to the left, we came, so that's this on the right is what we end up with our controller structure. And on the left-hand side, we see what we want to get. We use the desired polynomials here. And we've also seen that, well, we will not be able to cancel zeros that are outside the unit circle. So we have to leave them in. We have a remaining term of zeros that we would like to have. That's a BW tilde here, which comes from the controller afterwards. And then we said we'll extend by this observer polynomial. You see that we divide by the same polynomials, but deliberately we will not do the cancellation here because we introduced this polynomial to have sufficient order in the numerator to actually do a comparison of coefficients in the numerator, in the denominator, as well as in the numerator here. And for that, we need AO in place there. So essentially what we do is now we do this comparison of coefficients between this fraction and this fraction. And the first one, the numerator, is actually simple. The numerator terms are aligned, and we given or assuming that we choose AO somehow, we know BW tilde from GW actually. We know B minus, of course. We know the dead time. The only thing we don't know is F. And if we just reformulate this term here, Z to the minus D is on both sides, we can kick that out. Let's just do that. So that goes away. And B minus is in both terms, that goes away as well. So we just have a factor of Z to the minus 1, we just multiply that by Z, and we end up with a simple formula for F, for the pre-filter polynomial, which is just Z times known values, and AO is also considered known. We just choose that in the design at some point. Well, the numerator is easy, but the denominator is not as easy. We just take this, these two polynomials here, AW, AO, and the form that we got from our control structure here. And we'll come up with a method now to solve this equation, because what you see here is actually we have unknown coefficients in P tilde and in Q as well, and they are added together. That's convolutions here. That's multiplications of polynomials here and here as well. And so all these terms at each power of Z, they mix between P tilde and Q coefficients. And let's say on the right hand side, we can do the multiplication for each power in Z. But again, we have a combination here of polynomial of coefficients, and that's not easy to solve. In fact, that's a form of the so-called Diophantine equation. And we will show you now a short method of how to solve such equations in this form. Let's do that. We start by basically writing down the products in a clever form. This product here and this product, and also this product, are of course again polynomials. And we write down a vector form now basically, where row-wise we will sort out, or we'll connect each row to a particular power in Z. So let's see how that looks like for P tilde times A, and that's both polynomials. Now, if you multiply a polynomial, let's do that here. We have, for example, A was a monic polynomial, so we have, so A of Z to the minus 1 times P tilde of Z to the minus 1. That's basically 1 plus A1 Z to the minus 1 plus, and so on, plus A n Z to the minus n times P0 tilde plus P1 tilde Z to the minus 1 plus, and so on, plus P n P tilde times Z to the minus nP tilde. Okay, and this, of course, that's a lot of work now, but we can systematize that. Essentially, what you see here is we'll get results in Z to the power of 0 plus Z to the power of minus 1 times something plus Z to the power of minus 2 times something, and so on. And let's do that for the first few terms. So Z to the power of 0, we get 1 times P0 tilde and nothing else. Then for Z to the minus 1, we get A1 times P0 tilde plus, don't forget the second term, it's 1 times P1 tilde. And then for the quadratic, or for the Z to the minus 2 terms, we get, where do we start? We start at A2 times P0 tilde plus A1 times P1 tilde plus 1 times P2 tilde. And so it goes on, right? And now we write down this product here, and we collect it into a form where we have all the unknowns written out to the right as a vector, which are the coefficients now, p0 tilde until p and p tilde. And we multiply that by a matrix. Here we call this matrix capital A. And this matrix is composed so that as a result of this product, we will get a vector where all these coefficients are lined up beneath each other. So in the first line, we have c to the power of 0. We have here 1 times p0 tilde, right? That's exactly what we've just encountered when we did it by hand. Then for the next term, z to the minus 1, we get a1 times p0 tilde plus 1 times p1 tilde, and so on. And if you do that systematically, you will get this structure that is written down here. It's a certain form of, yeah, it's actually a Toeplitz matrix, I think, or it's Hankel. I always mistake those two. But basically, you get a certain diagonal structure here in this form, and we do that for the other pair as well. We get q c to the minus 1 times b minus c to the minus 1. Q is unknown, or the coefficients of q are unknown, and the coefficients of b minus are considered known. We will know them afterwards. So what we do here now is again the same. We get to a form where the q vector here contains all the unknown q coefficients, and b minus matrix contains now the correctly aligned b minus coefficients. So that's the same story as above. Now it's the only difference is that we don't have a 1 here, but instead b0 minus. B0 minus is non-zero. That can be, there is some value in it, because it's numbered differently. It's the b minus polynomial, not the b polynomial. Okay, now once we've done that, on the right-hand side, if you look up, what we wanted to do is actually now we started writing down this first term here, then the second term here. We have to shift that afterwards correctly. And now what we still need to do is this matrix, this coefficient convolution, or this product of polynomials here, AW, AO. And by doing that, in the same fashion, actually, it's just we express that, or we write it in shorthand form. It's known, both of them are known. So we just do the convolution. Essentially, it's the same as we did above when we did the multiplication and collected for alike powers in C, and then we correctly align that and we get this vector. Now, we can actually reproduce now this equation that we got up there as a vector equation. This equation here, this one, is a polynomial equation as we wrote it down in 435. But now we restyled it, we transformed it, and we write down a system. So it's a vector equation now with this term and the next and the next as a vector equation. And if all these vector equations are fulfilled, that means that all the coefficient relations for the particular C powers are fulfilled. So also the polynomial equation up here is fulfilled. So we substitute, or we go from one particular form, this Diophantine equation, we unroll that into many vector equations and attempt to solve them. And by doing so, we establish the solution for the original problem. One more thing, we can split off. You noted maybe that here we have a separator here, a separation line, and P0 tilde is in fact equal to 1. We already knew that. That's why we have this separating line and this separating line here. So we can actually exploit that and insert essentially that P0 tilde equals 1. And that's what is done here. Right, and then additionally, if the controller now is required to have integral behavior, then what we know is that P tilde at c equals 1 has to be 0. That's essentially when you look at the controller transfer function. Look at that here. The controller transfer function is here, is divided by P. Okay, and now if this controller should contain an integrator, then essentially this P polynomial should have a root at c equals 1. That's just the integrator pole that we would have to add in. And if you write it down, it's a nice finger exercise if you want to do that, or maybe in the exercise, you will see that as well, is that this means then that P tilde coefficient values have to add up to 0 in that case, to have an integrator in the controller. All right, now we write down all these equations that we had before in a matrix vector notation, and that looks like this. We come up with the term A, this matrix A, which is multiplied by P1 tilde until P and P tilde. Then we have zeros, then we have B minus, and we have zeros. And these zeros, they basically account for the shift due to the dead time. D is in here as the number of rows. So then we have B minus, and this portion here, this right portion of this matrix is multiplied by the Q unknowns, by the Q coefficients. And in these first couple of rows that come out here as a result of this multiplication, we will get AW convoluted by AO. So that's what we had on the right-hand side. And we have split off the term with P0 tilde, which was equal to 1. And if we do that, and it was the leftmost column here, and we multiply that column by 1, which is exactly this column, and subtract it from both sides of the equation, so we get this subtraction here, and additionally P0 tilde is eliminated here. So we get in the first bunch of rows A times P tilde equals the correctly shifted B minus times Q, plus B minus times Q equals AW convoluted with AO, and then this correction term. And additionally, what we just mentioned before, P tilde at c equals 1 has to be 0, is now added as a last row here. P tilde at z equals 1 means that essentially we set z equal to 1 everywhere. And then what you do is you just add up all the coefficients in P tilde. And they have to amount to 0 in total. What does that mean now? We know already that P tilde 0, this coefficient up, which used to be up there, is equal to 1 because it's a monic polynomial. So we have this 1 plus all the other coefficients, and they should be equal to 0. Okay, and this last equation is now coded here. We take all the other coefficients, P1 tilde until P tilde and P tilde here times 1, each of them. That's this term here. The Q's don't play a role, they are zeroed here. And then on the right-hand side, we have minus 1. Why do we have minus 1? Well, that's just the value of 1 times P0 tilde here. And P0 tilde was 1, so we put that to the other side, becomes minus 1. And this system of equations here, the right-hand side is entirely known. That's all coefficients that we come up with directly from the model and from choosing AO and from knowing AW and BW. Then this big matrix here, A and B minus, all these entries, these diagonal entries can be built up also from model knowledge. And then we have a big matrix that we know times an unknown vector equals a right-hand side, which we also know. Written in a compact form, it looks like this. M, some matrix, times this unknown vector equals V. That's a linear system of equations. And we potentially can solve such a system quite easily with MATLAB especially. Of course, you can do it by hand, but that's not useful here. You will do that by MATLAB, of course. All right, but in order to do that, what we want to have is actually a unique, exact solution. And that means that essentially, if you remember linear algebra, simple case, if you have such a linear equation, then what you want for a unique solution, what you need to have is that M is a square matrix and that it has full rank or its determinant be non-zero. And then you can actually solve directly by inverting M and multiplying it with V, and you get the solution vector. And there are tons of other methods depending on the size and structure of these coefficients, how efficiently you can do that. Gaussian elimination is a simple method, a simple systematic method that you learned on pen and paper. But of course, I mean, that's basically what MATLAB is built for in many ways, or is everyday job for MATLAB. So essentially what we need to do is to prepare the problem here by compiling this matrix M and the right-hand side vector V in such a way that it's correctly sized in a square sense and also that it's invertible, and the rest is done by MATLAB. So essentially, when you now look at the size of M, we had a bunch of sizes written up here. That's always the sizes of these blocks or matrices that come in here. And it's always row dimension times column dimension. And now if we put that all together, we see that the matrix M here is of this size, np tilde plus n plus 1 times np tilde plus nq plus 1. And now we see, in order to make that square, n has to be equal to nq, obviously. That's the first rule that we can read off here. Then the vector p tilde, sorry, that should be a tilde up here, p tilde q is of course np tilde plus nq plus 1 high. nq is starts with q0 here. That's why there is a plus 1. Okay, so we have np tilde and then we have nq plus 1. And of course, this number of rows in this vector should be the same as the number of columns in M, which is the second dimension here, np tilde plus nq plus 1. Okay, but that's the case anyways. And then also what we need is that np tilde plus n plus 1 should be, that's the first dimension of M, so the number of rows. That should be the number of rows in V here, and that's that can be obtained from the sizes of AW and AO. And actually that tells us about the order that we need in AO, for example. Also, if you look at the structure up here, these blocks, or the row dimensions of these blocks, they must not be negative. They can be 0. If we don't have additional dead time, then this one is gone. This one could also be gone, but it cannot be negative, otherwise it doesn't work out. So we have an inequality now that this expression here has to be greater than 0 or greater or equal to 0. And that's exactly this second rule. That's what we have to check. And by that, we get a lower bound for the number of p tilde polynomial coefficients. So then we get from here, we get equality, that's this one here. And also NAO should be at least 0, then we don't have an observable polynomial, or greater than 0. And to do that, we get this inequality again. So all these 4 inequalities have to be met. And from these inequalities, we'll get some hints, some rules of what order we should select for the P, for the Q, and for the F polynomials. All right, so let's put that into some practical use. Yeah, some side note, if you don't need integration in the controller, if a proportional controller is enough, for example, if you have integral behavior already in the plant, then you get a modified condition 438. This first one is not, it does not tell you that nq equals n, but nq equals n minus 1 only. Okay, yeah, so the structure of these matrices is called Sylvester matrices. Let's look at that in an example, 4.6 here. We have a general structure of the plant here. So we have B, the B polynomial of second order here. We have the A polynomial here as well of second order. And we have 2 samples dead time here additionally. So now what we want to have is a model following controller should be designed with integral action. So we want to have the integrator in the MFC, and it should come up with, we want to come up with a W with the closed loop denominator polynomial of this form, and we can consider these coefficients known. That's usual pole placement. And we also assume that the numerator polynomial here can be written as, well, c to the minus 1, of course, we pull that out. And then we have 1, 0 here, which is inside the unit circle. And then we have another factor here. So we can identify B plus and B minus here. Take care, we always need B minus, even though it's a static number here. It's not a polynomial, or it's a trivial polynomial in Z. So there is no C to some power other than 0 here. But since this is a monic polynomial, all the scaling, if you have some other factor, some scalar factor in B, goes into B0 minus. That just ends up here. Okay, now we choose our desired polynomial. It should look like this. So it should be B minus, BW1 times C to the minus 1. Then we take the dead time with us, and we have our desired polynomial in the denominator. We want to have tracking, and in that case, we can say that GW of C equals 1 has to be equal to 1. That's the closed loop transfer function, and if the closed loop transfer function, if we wait long enough there, and its value becomes 1, then we know that we have tracking. It means that a reference step is fully followed. So we do that, and by doing that, we get this additional condition, if you want. So basically, BW1, you see that we substituted Z with scalar 1. So essentially, this function of the coefficients has to be fulfilled, and you can eliminate one of the coefficients, for example, BW1. By that, you can determine the value of BW1 to rescale the system so that you get this desired reference transfer function gain. Okay, now when we start now with the, now we established what GW should be, and we made our split up into B plus and B minus. Now we also can identify that BW should be, looks like this. It's BW tilde times B minus. And in our case, B minus is B0 minus. And then BW tilde is, so we want to have this BW1 here. So we write down BW1 divided by B0 minus times B0 minus. They cancel each other. So we established that BW is really the BW that we want. But we can identify BW tilde as this part here. So that's what we'll use in the design. Now we need to establish which orders of the polynomials have to be there. So first of all, we say we evaluate all these rules, these 4 equations. So we get NQ equals 2. Then we have NP tilde should be greater or equal to 3 when we insert. So we choose this smallest possible number, NP tilde equals 3. With that inserted, we can obtain how large the observer polynomial should be, which is 3 in this case as well. And then we check this last inequality with NP tilde equals 3, and it's okay. So now we know that we need a third order polynomial P tilde, a second order polynomial Q, and we have an observed polynomial of order 3 as well. We can construct all these by hand, basically, all these polynomial multiplications. We'll shortcut that a little bit. We get to these coefficient matrices times the unknown vectors each, put together AW convoluted with AO on the right-hand side here. That's this long expansion here. And then after some manipulation and reordering, we basically get here on the top, we get the entire equation here in a matrix vector equality with a vector right-hand side as well, of course. And P0 tilde is not yet eliminated. And if we know that P0 tilde is equal to 1 now, we can eliminate that. We multiply. We take this this first column, multiplied by 1, and subtract it, put it on the other side. So that's essentially the second equation here. And that's the design equation that you can solve for these unknowns here. And once you have them, you have the controller. This example was supposed to show you this general structure that you can see a little bit with numbers how this construction looks like. Let's go to some actual numbers, some actual design. We take a continuous time transfer function here with 2 real poles. We add in the zeroth hold and sample at 0.1 seconds. Then we get the Planck transfer function in the Z domain as so. We want to have an integrating MFC so that the denominator of the closed loop transfer function becomes a certain second order polynomial that can come from specifications, for example. And yeah, these specifications are that you want to have a natural undamped eigenfrequency of 4 radians per second, and a damping ratio of 0.7. Now, if you look at the numerator polynomial of the Planck, so see that we do not start out directly by prescribing some BW. We first look into what BWs we can actually prescribe. So we analyze the Planck numerator here. We split them up. So basically we extract the factor c to the -1, and then we put it into this form so that you get 1 plus something times negative powers of z. That could be higher order as well. And then the rest is factored, because we wrote 1 here, this factor is actually B0 minus. To have no position error, again, we want to have GW of 1 equal 1. And so we choose our closed loop transfer function like this, that we want to have. And by doing that, that actually comes from the fact that we will get, when you insert z equals 1, you will get 0.12 divided by yeah, 0.12, it will be there. All right, so now we see that BW should look like this, and we want to have a factor of B minus in here. This factor is 0.045, so we get 1 over 0.0453 in here. So this 0.12 divided by B0 minus times c to the -1, and that's our BW tilde. Okay, now we prepared the design. Again, we go into the conditions for solvability in order to get to our orders of the polynomials, NQ and AO. We get to NP tilde, which should be at least 1. We take that, and we manage to satisfy all the conditions like that. Now we have a first order polynomial NAO, and we can actually choose any stable pole there. We choose it fast enough, of course, in comparison to the Planck transfer function. We choose some pole, it could be a different one. That's subject to tuning as well, but choose just a stable polynomial with sufficiently fast poles here. So we choose AO as a monic polynomial of the required order. Then we come up with all the equations here and solve the system of equations, and we get to these polynomials. And now let's analyze what we actually got out there. Yeah, the pre-filter is, of course, then in the end, it's obtained easily when AO is actually defined, which is this guy here, and the B terms, and then we get this F polynomial. Now, when we realize this entire transfer function with the MFC now, you can do that in Simulink, for example, or just do some algebra and come out with the transfer function itself, the closed loop transfer function. And we simulate that, look what we get. At the output side, a step response looks perfectly fine. So we get diminishing, so this one is the step response for reference, and this one is the disturbance step response. This is very fine and looks good, and actually complies with the specifications that we wanted to have. But on the other hand, if you look at U, at the control input, we see something wild going on, and we see ringing here. Okay, so that's really, it's basically something which is more complex, which is somewhere in the middle here, as you could say as an average value here. But then about that trajectory we'll get changes of sign. And that, of course, as we discussed before, cannot really work well in most practical applications. The question is why that actually occurs. And if you look at the transfer function from W in a closed loop, from W to U, you see actually that you will get a pole here, which lies at minus 0.9. And if you remember in our pictures of the first order and second order responses, in the beginning of our lecture today, we said that poles with a negative real part, especially if they are close to -1, they produce ringing. And that's actually, this 0.9 is actually the decay of the ringing amplitude here over time. So we want to avoid that, obviously. And the key to success here lies in our choice of B-. We do an alternative design, for example, here, by not taking this pole into B+. That pole was actually included in B+. If you look up there, B+ was this here in the middle, this one. And that's exactly the pole location of the ringing behavior that remains. Okay, so now we take care not to put poles that may come, or zero locations that may produce ringing, just as we avoid putting in unstable behavior there, or all-pass behavior in that sense. If you have zeros outside the unit circle, you will not put them in B+. And you do the same basically with zeros that are close to ringing, that are close to -1. And by doing the design once again with B+ only equal to 1 and B- carrying all the rest, so that's now, that contains the ringing pole now. That's now we go through the design again, we get a little bit different conditions here. So we have to choose, for example, a second order observer polynomial here. So the design gets a bit more complicated. The controller is a bit more complex in that sense, has more dynamics. And we choose it here as poles at -8 and -10, and we put them into the Z domain, and that produces our observer polynomial. That's only internal dynamics. That will not be visible to outside. We just should choose stable and sufficiently fast poles here. Now we do the design, and yeah, the polynomials look a bit different, the order is a bit different, and what we get is virtually the same responses for the outside world, for the reference step response and for the disturbance response. And if we look at U, now everything is nice, everything is smooth and actually as we would like to have it usually. And this ringing behavior is just gone. So it was just an unfortunate constellation before, where we produced ringing inside, which was cancelled again. So it was not visible to the outside signals, but in the internal signals it actually came up, and that's dangerous in an application. So there are scripts online, or will be online, for designing an MFC or helping you with the design of an MFC. And what you should understand from this lecture is basically go through the material, check if you understand this result. You don't need to manually solve the Diophantine equation. That's not the point. The point is really to make yourself comfortable with the design, with the design ideas, and to reflect about what you have to choose in the design. For example, how these conditions come up that you have to check, and you have to come up with the orders of the particular polynomials that come up here, and just exercise on some examples to do an MFC